Why am I evil? Why? Okay, well, great start. This also, okay, this is EE, but don't look at this. This is not what we're doing first. Oh god, everything's all over the place. Okay, hello, hi, hey everybody. I just want to get right into it because I'm not going to edit this VOD that much. Hi, I'm Damie. I am a little cat boy, and I am doing these little speedrun streams, as I call them, because I want to prepare for finals, but I also want to help people kind of get a little bit of an intro to some course material, or maybe just conceptually review some of the course material, or, you know, if you've never heard of electrical engineering or dynamics or anything before and you kind of just want to mess around with it, that's what today is for. So I'm gonna edit out any of the Mike Demon moments, just so we are aware of that. You guys don't worry about it. Don't worry about it, VOD viewers. I'm not gonna take questions that aren't related to EE stuff today. I have some problems that I have lined up. I have a FET simulation because, I don't know, I really like FET simulations. Yeah, we're just gonna hang out. I don't really know how long this is gonna take. I have to get my notes up, actually. Whoopsies, teehee. I don't think it's gonna be that bad. Okay, we have... Oh my gosh, you're raiding with people! Oh no! Wait, now I have to be good! Now I have to be a good lecturer! Oh my gosh, thank you, Instucky, what the hell? This is a great day to raid! to stick around if you want. We're doing an EE speedrun, any percent, hopefully like 90% speedrun, of my 10-week circuit theory course in a couple hours. So we'll see how it goes. Gonna teach some stuff, gonna talk about some stuff. I did not expect there to be people here. That's so nice. Oh my gosh, you guys are so niceies. Hells yeah. Well, I guess we can just get into it. So, in talking about like kind of prereqs for this, the prereq for this course was Physics 3. I don't think you necessarily need to know all of Physics 3. I think most of it is for the circuit stuff from Physics 3, which, just to kind of overview, would be knowing like what resistors and capacitors and inductors are, knowing more about sort of the properties of those devices, kind of how they work, right? So like, we'll talk about you know, capacitance and inductance kind of stuff when we talk about, mostly when we talk about AC stuff, but just sort of knowing that those devices exist, what they do, knowing like what voltage and current are, Ohm's law we're going to be using a lot, Kirchhoff's laws, my boy Kirchhoff. But so with physics, we kind of tend to think about the components themselves, right? So it'll be like a resistor or something, and we're trying to figure out maybe the voltage over the resistor, or we're trying to calculate a resistance, right? If we know that there's a voltage and a current and we don't know a resistor. But in electrical engineering, we care less about the components and we care more about the circuit as a whole. So it'll be something like, okay, well, we have a bunch of resistors, we have a bunch of inductors or capacitors or whatever it is, components, and we put in a voltage and we want to know what the current is in a certain place. Or we'll say, oh, we want to know about, you know, the voltage at a certain place. Those are kind of our basic tools, and that's what we're gonna start out learning. So we're switching from thinking about components, like, so we're not gonna, you know, when we would do Ohm's law or Kirchhoff's laws in Physics 3, we tended to do like, okay, the voltage over this resistor, the voltage over the source, we add them together, they should equal 0. But we're gonna say the voltage at this point instead. And so it's gonna be a lot about point-to-point things and nodes and that kind of stuff. So, I mean, I guess we can just kind of jump into it with the first topic, which is node voltage analysis. It's great. I love names that make me feel like I'm in the Matrix. This is it's a fancy way of saying something that is not that hard. Essentially, well, I guess we should just start with what a node is. So when you have a circuit, you got a lot of stuff. Let's say you have like, I don't know, a little dude here and there's another little dude, and these are just, doesn't really matter what they are, they could be whatever, right? Components. There's like another one here, right? You got like, I don't know, a resistor. They can be connected kind of however, you know. But we want to define a node as, it's very similar to a junction from physics. So it's going to be where things meet up, components meet up. But generally, we'll probably mostly talk about nodes as, instead of just 2 components connecting, as like 3 components connecting. So while, you know, you could kind of say like that this is a junction, you know, it's better to talk about like this being a junction, right? Because like there's 3 things connecting here, and we have, you know, a node there. It's not that, you know, a junction is not a junction if it's 2 things, but it's just kind of like, it's not gonna have like voltage like that's super interesting. So we care about these bigger nodes. And you can like have these things called supernodes, where like if you you can have nodes like with the same voltage, and they are called a supernode, but it doesn't really matter. You don't really do anything with them. So in our cases, we usually care about 3 things connected. You might get 4, like if you're lucky, but it's probably gonna be 3. Okay, so what we want to do with node voltage analysis is kind of, as the name suggests, we want to find voltages. So if we have a circuit, I don't know, let's just say it's there's a lot of resistors here. I don't know, there's a lot in here. They can look however. Something that's not, you know, necessarily just like series and parallel, because, you know, as we know from physics 3, you know, we're going to use like series and parallel tactics at some point, right? Because we know things are in series or in parallel. But sometimes we'll have circuits that are really complicated, and we want to just be able to have kind of a fallback way of analyzing voltages instead of like combining everything into an equivalent resistance and then, you know, doing that. So let's say like our motivation here is we want to find the, well, this doesn't really have a, okay, let me put another one in here. There we go. Kind of a weird circuit. I'm iPad Kid maxing. So let's say we want to find the voltage at this node, and let me define a ground. There's gonna be grounds in these circuits, and for our purposes, a ground is just gonna mean that wire is 0 volts. So when we say like, okay, we'll say that there's 0 volts here, and then maybe this source is 5 volts. That means that this bit right here, this node right here, is gonna be, right, 5 volts plus 0 volts. And that's sort of something that we know from physics 3, where like the voltage over this is 5 volts, right? So if we're trying to find the node over here, the voltage of that, how we're gonna do this is we're actually gonna use Kirchhoff's current law, which is a little silly because it is node voltage analysis. But we're gonna essentially say that the currents going into the node, so current in, equals the current out. And you can also write it as like current in, you know, plus or minus current out equals 0. Either one is fine. I know some people who like to keep the signs whatever way. There might be some weird sign stuff that you have, because we're gonna have to talk about sign convention for sure. But I kind of like to do in equals out, just because then I don't have to worry about sign conventions. So the way that we're going to define current is from Ohm's law. We're going to say current equals the voltage over the resistance. So for every component. And in this case, it's a little interesting, right? Because what is our voltage going to be? How are we going to define that? What we're actually going to do is define it as, we're going to say like voltage 1 minus voltage 2 over the resistance. So our node voltage setup is kind of going to look like that every time. And our voltage 1 is where we start at, and our voltage 2 is where we go to. So if we were trying to say that this current is going in here, and then it goes out here, it goes out here. And this is not a great example because this is like a super node, right? There's no component in here, so this is going to have the same voltage, right? Because like we say this is 5 volts, we keep going along the wire, it still stays 5 volts on that wire until it hits something, right? And this one too is going to be, yeah. So we would say if we want to try and find the voltage over the source, if we didn't have it, or just sort of say it as a general thing, let's say we knew the voltage, you know, just be V2 here, we would say, okay, 0, so that's our starting point right here, 0 minus V2, and I don't know if this was a resistor, that'd be a resistor. Don't worry about that. you wouldn't have that. You might have like a current source, right? And then we could just say the current going in there. Yeah, so that's like the basics of node voltage analysis. We're going from point to point, and we're defining the currents over 2 points, and we need to use the resistance of the component. If you don't have some stuff, it's going to be a little harder to do. Like if you have a current source in there, like you might have to think about that a little bit, but it shouldn't be too bad. Let me grab this actually, wait, why am I doing this? This example doesn't even have the numbers there. Ooh, getting there. This is a no scuff at all here. No scuff here, folks. Here we go. So here, this is a pretty like common node voltage type question. So we have a circuit, and let's write in the voltages and stuff like right by it, so I don't have to keep checking. So we got a 12 volt voltage source. We've got a 5.15. That's kind of annoying, but whatever. We have 3.05, 4.3, and 5.1. So they're asking us for the voltage over AB. So in this case, we're going to have to find the voltage at A and find the voltage at B, and then we're going to have to subtract them, right? So you can actually, like, you could do this a couple different ways, right? Like we could do this by combining them in parallel and then combining them in series, both, and then combining them in parallel, and then finding an equivalent resistance, and then getting a current, and then, you know, maybe doing a current divider or something, or just, you know, solving for the current over them. But we're gonna try and do this with our node voltage analysis. So first we gotta pick a ground. So let's say that this is the ground down here. It doesn't actually really matter where you pick your ground. But now we're just gonna go, and so we've got a node here and we've got a node here. Okay, those are the two nodes that they gave us. Sometimes they won't, sometimes they'll give you nodes, sometimes they won't give you nodes, sometimes they'll give you one, but you need to find another one. Again, it kind of doesn't, if you make too many nodes accidentally, it's okay. You'll figure it out when you go through it. So like, for example, when I was just looking at this, because again, I'm doing this right now, so it's been a while since I've done node voltage analysis. I was like, oh, well, let me put a node here, and then put a node here. It's like, okay, so if I put a node there and there, well, these two nodes would be the same, right? Because this is one wire that they're connected by. And so that would just continue being, you know, whatever voltage that is. And then if you look at this node, we can say that this node is going to be, well, okay, maybe, let's leave that node there. Getting ahead of myself a little bit. Let's just do R2. All right. So where do we start for R2? Well, we go from the ground, and we're gonna go like up. I haven't picked any current directions, but let's just write R2, so the voltage of R2. So the R2, the current of R2. Current of R2 is gonna be 0, right? So we start with 0, and we're gonna say minus VA. So we're assuming the current is gonna go this way. I don't know, I just assumed the current would go that way. And then it's gonna be over the resistance of R2. So now we have to kind of figure out what we actually want to analyze in terms of our node that is doing or place where we're adding the current, right? Because right now with these two spots, they're not really giving us, you know, they might be nodes, they're just two component nodes, but it's like the current going in is just literally going to equal the current going out, right? That doesn't really help us that much. So we need to find a place where the current splits. So let's say that, I'm actually gonna not draw this way for right now, but that's how we do it. I'm gonna say that I think that the current comes over here from the source, and it's gonna split down this way and down this way. So what that's gonna kind of look like is we're gonna say like the current, we can call this I1, This one's I2, this one's I3. So we're gonna say like I1 equals I2 plus I3. And I'm writing that as the ins and the outs. So in our case, then we just have to start putting stuff in terms of our node voltages. Now our current is going to be the same in both these branches, right? Because sorry, not the same in both these branches. It's going to be the same like over these two resistors because they're in series. So throughout these branches. But we'll worry about the specifics later. Let's just try and get this in. So for our first one, we have. Oh, never mind. This might be kind of a gross place to do that. I'm gonna skip the source. We're gonna do the other ones right now. Hey, how's it going? Doing EE speedrun today. Okay, so we're gonna say that the current through here is gonna equal the. We're gonna start. So we start at 12 volts. So this up here is 12 volts because we go along this wire, and that keeps being 12 volts. 12 volts minus VA. I'm just gonna say over this. Over R1. And then the other one is going to be, we actually also start at 12 volts, so 12 volts minus VB over R3. Now, in terms of the I for the voltage source, we kind of can't get away from that. Right, there's no... Can I ask you a question about integrals? I am doing electrical stuff only today, but if you want to ask in the Discord, you are more than welcome, and I will definitely answer it after stream. Sorry, it's just a little weird day today. Okay, let's see. So for this voltage, we might have to do we might have to combine stuff. Well, okay. Okay. This is a good review. Okay, we're gonna combine the voltage source here. We're gonna combine all the resistors in series and then in parallel to figure out what the value of the current is over in that left loop, which, you know, it would probably just be smarter to find the voltage over a resistor, but we're talking about node voltage analysis, so we're not going to do that. We're just going to do it the hard way. It's okay. So we'll have R3 plus R4 in parallel with, sorry, I'm just doing it here, in R1 plus R2. And this is upside down. And then that's going to equal, our current is going to equal V over I. You know, classic number that everybody loves. I'm not going to plug that in, but that's what our current would be. So in this case, this is just going to be like a number. But you can see we have two variables in this equation. It's two unknowns, and we only have one equation, so we can't solve this. So we actually have to find we have to use the other node right here. So in this case, we're gonna have, let's say this is gonna go down here. We gotta be consistent with our signs. It doesn't matter which way you choose, you just have to be consistent. And what does matter is that this arrow, remember, defines the direction we're moving across the resistor. So in terms of both of these, we're going from top to bottom. So we have to pick our starting point at the top and go down to the bottom at our ending point. So for the other one, we'll have I, and conveniently, I guess, oh, well, that's probably not right, because they're all going in, but that's okay. So we have I1 plus, so we'll have VA minus 0 over R2 plus VB minus 0 over R4. Right, so we just did this and this, and that and that. Wait, I lied, this one goes out. Why? We said being silly. There we go. And so, Damie, how do you not have women just throwing themselves? I don't know. Is this not like the best thing you've ever seen? Node voltage analysis, baby. What more could you want in a man, really? We can set these equal to each other, because these are all, like, I mean, this can equal this, and then we can just solve for stuff. Does that work? I don't know if that works. That like will probably work. If not, just do the other way. But yeah, that's the basic idea of node voltage. So we take the currents and we add them up. The second half, or not the the second analytical technique that's sort of the parallel to this one is the mesh current analysis. So what we're going to do is we're going to use Kirchhoff's other law to do this one. Mesh. I don't know where it cut out, but we're gonna. So you've probably heard that that you have loops in a circuit. So what causes the microphone demon? You know, for all my engineering knowledge, you know, you'd think learning electrical engineering and like frequency and, you know, interference, which is what we're gonna talk about later, that I'd be able to figure out what causes my microphone demon. I don't know. I think it just hates me. I think it's pure spite. It's particularly spiteful lately. Maybe it's the final season that's really getting it active. It feeds off my negative energy, I think. Anyway, so all meshes are loops, but not all loops are meshes, which is kind of a weird thing to say. But the way that we define a mesh is that it is a loop that does not contain any other loops. So for example, we have this loop on the outside, right? That is a loop, but it's not a mesh because there are other loops inside it. But if we look at one of these little loops on the inside, that is a mesh because it doesn't have anything else inside it. So when we do mesh current analysis, we're going to assign a current to each one of the loops. All right, and we just sort of choose okay, that was negative, but I don't know, you could choose whatever direction you want. Maybe choose counterclockwise because that's positive in the right-hand rule system. But it doesn't actually really matter here because our sign conventions can be a little bit different. So the one thing that we have to know about mesh current analysis is that if we want to find, so over here, right, this current is just going to be, let's say this is I1. The current in this wire right here is going to be I1. But if we want to find the current in this, we have to say, okay, so I1 is going up here. And in this wire, I2, if this is I2 is going down. So what we have to say is, for this one, the current equals I1 minus I2. And when I say like I1 minus I2, the signs are going to be more dependent on which one is winning, like which one is dominating. You know, so if you have a really strong I2, you know that it's going to go down because the I2 is going down. So generally when I tend to do this, I don't really worry about the signs that I get for something like this, and I have to just kind of like logic out like, okay, well my I2 is going this way, my I1 is going this way. Because when you do the analysis, you might get negative numbers, right? Which just means that you chose the wrong, not really wrong, that the actual current, you know, is maybe going this way. And then so if we have that, then they would add, you know. Just do whatever you need to keep track of the signs. I tend to like to kind of pull back from leaning on the math to handle signs for me, at least for electrical engineering stuff, because I think that it kind of causes some headaches sometimes. Okay, so I think that's all we need to start doing mesh current analysis. It's based off of Kirchhoff's what is it? Voltage law, or like loop law, I guess. So we're gonna say like the voltages, the sum of the voltages in a loop or in our mesh are gonna equal 0. So if we go across this, we will say like maybe there's a component here and a component here, right? And like a component here or a component here. We're just gonna say like, okay, as we follow the current, R1, R2, R3, we say this will be I3 times That's just the you blink and you miss it, you know. I give you a break in me talking so fast. So we do I3 minus I3 times R1 because it's a resistor, so we're actually going to get a voltage drop across the resistor. Again, the signs, you can either make all your resistors negative or all your voltage sources negative. I tend to just like to make my resistors negative, even though it kind of like results in a lot of negatives. But to me, that's what kind of makes sense conceptually. We're stepping down in voltage over a resistor. And then, you know, times I3 R2 minus I3 R3. And then for this dude up here, we're actually going to say minus R4 times, because they've got two currents going through them. Right, so in this one it's going to go this way, and in this one it's going to go this way. So we say R4 times I3 minus I2. Yeah, I agree, that's my intuition too. Yeah, I think stepping down over the... But I know some people don't like writing it all negative, and so they just write the voltage source, which I can also kind of understand, but I feel like it's a little bit more confusing. Okay, so for this example, I'm going to set this one up. I'm not going to be solving like any of these. Dude, I really wish we just standardize on electron flow rather than conventional current. My god, I agree. I think the worst thing was doing physics 3 and doing circuits like for, you know, a month, whatever, and then going, oh yeah, but for inductors, just forget everything you know about sign convention and just you need to do electron movement. And it's like, man, oh, come on, please. Like the meme is like the world if blank, the world if electron flow was conventional. Makes semiconductor stuff easier too, yeah. All right, so we got, they're giving us the directions here, so they actually define them this way. So we're gonna say, ooh, my brain just stopped working there. Okay, we're gonna start with the first mesh over on the left here. So we'll say VS, and we just keep the VS because we're adding voltages, minus R1 times I1. And the next component we have is minus R2 times I1 plus I2. See, they're going in the same direction here. This one's going down, this one's going down. Minus R3 times I1. Equals 0. And then for the other one, we'll have IS, which is kind of unfortunate, actually. Is there the... Okay, is this a superposition question? No? Okay, well... It's funny. Oh, wait. No, we just know I2. I2 equals IS. Sometimes they just give it to you, and then life is great. Because we know that this current is going to be around here. So the weird thing is, like, with the mesh currents, like, it's sometimes a little hard because, like, if you think about this, it's like there's a current divider happening right here. And so it's kind of weird to just be like, oh, well, you know, I2 for that loop equals that. But because we're doing superposition for our components in the middle there, like R2, we don't have to worry about that because it kind of takes care of that. It's kind of the same thing, like if you were to just and this is kind of a spoiler for something we're gonna do later, if you were to just take out one of the sources and figure out the current going through it because of that one, or take out the other source because of the voltage going through it, and then superimpose them, or superpose them on top of each other. But yeah, so then you just have to solve this equation. It's one unknown, you know, it's not too bad. Just plugging stuff in. All right, let's see. What is next? I don't remember anything. I think it might be. Oh, okay. Literally the best segue in the world. Superposition. Let me grab this image. So when we talk about, this is important. When we talk about voltages, or we talk about currents, at least like for this scope of things, we're going to be talking about them as like linear functions. And because we're talking about them as linear functions, that means that we can do the classic differential equations tactic, or the classic first grade math tactic of adding things or subtracting things, because they're linear and they like to add with each other very easily. It's called superposition. Like if we take one thing and we put it on top of each other, basically. It's the same idea as creating a homogeneous solution and a particular solution for a differential equation. That might make it more complicated to understand, but so what we're going to do is for particularly hard circuits, or for circuits that we don't really want to have to deal with using, node voltage or mesh current, because it's just like a real hassle. We can just take it apart essentially and then put it back together after we're done with it. When you said the classic differential equations, the tactic, I thought you were saying guess the answer. That is true. We can also just do that. I mean, I wouldn't suggest it, but it's certainly a thing you can do. Superposition is like a superhero, but for engineering. Oh yeah, it's like it starts to become in a lot more things. What was this one asking for? I didn't write about what it was asking for. I'm gonna guess it was asking for the current through something due to something. Power supply. Wait a second, I just want to see what it's asking for. I guess maybe I just thought we could do it. I don't think I. Okay, this is a good example. Like, let's say. Let's find the current through the resistor due to only the voltage source. So the thing about superposition that we have to just keep in mind is that depending on the type of source, we have to put different stuff in there. Which sounds a little weird, but like we want to essentially like get rid of the source, right? We don't want it to keep existing. And we want to do that in a way that is smart. So what we're going to do is we're going to replace our voltage sources with shorts. I'm pretty sure. So voltage is stored over gap, right? Voltage is just the buildup of a potential difference, i.e. there is electrons on one side, no electrons on other side, or more electrons on one side, right? And so if we were to cut the voltage source, then we would still have potentially that gap, right? But the only way to get rid of it is to replace it with just a straight up wire. And it kind of makes the sense for current as well, because we're going to replace it with an open circuit. I'm pretty sure. Let me check. I just want to make completely sure. Where is this? Okay, that's Thevenin. We're not going to talk about that yet. Yes. No. Yes. Yes. Yeah. What I said. Because of what I said. So like to get rid of voltage, we're gonna go shloop, and then to get rid of current, we're gonna go shloop with our scissors. Those are good enough scissors. Okay, so let's just say, because we know we know what the current through the resistor is due to IS. We know the mesh current, I guess. That's we don't know because it's gonna be a voltage current divider. But let's do the voltage one first, just so that we can see that. So we go in here, and we're gonna redraw the circuit, and we're just gonna replace that source with an open deuter right there. So it really doesn't do anything, but so then we just have to find the I, so I2, and some people call it prime because, like, I don't know, differential equations, you like add the primes or some, I don't know. I don't know why they call it prime, but they call it prime. And they call the other one double prime. It doesn't really matter which one you do. It's gonna be Vs over R1 plus R2 plus R3. And let's be really clear about the direction it's going. It's gonna go that way. So then if we do the other side, we're gonna close up this side. Boop, 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 boop. And we'll have our current source over here. And so I2 prime, double prime, I don't know, whatever. Sometimes I just will call it like 1, like a subscript 1, 2, whatever. To find this, we gotta do, combine these two in series, and then this one in parallel, and we can figure out what so we'll have the voltage, so it'll end up being R2 times, we're gonna combine those two in series and then combine them in parallel to get the voltage. The voltage is gonna be the current, so it'll be I2 times, I'm sorry, I'm trying to like do this all in one step. The current times the resistance, so it'll be 1 over R1 plus R3, 1 over R2, and then minus 1, and then this is our voltage, and then to find the current through this. Evil mode, yeah, me when I'm, evil, I do superposition. The answer is 6. No, I'm evil, so I don't plug in any answers. Wait, no, that's what I do. That's not evil. I love numbers. I only do calculations. No explanation necessary. We just put it in a calculator. No, it's 7. The answer is always 7. Okay, current. I don't really know. I think it would like split. Okay, it's kind of important that we know the direction of it actually, because when we superimpose them on top of each other, we need to know the direction. So you could actually also do. Wait. Yeah, you could also do. I was gonna say you could do mesh current, but that would be kind of weird to do without multiple sources. I think it goes this way. Because it's going that way. But when you do out like the math, you can figure out the direction. And then we just when we want to figure out what I2 is, we just say I2. And I'm assuming that we've set our signs correctly on our little chunks here. So we're just going to add them together. And then if one is in the opposite direction, then, we go in the opposite direction. If they're in the same direction, we add them together, just like pizza pie. And that's superposition. I think a really great time to use superposition is if they ask you for superposition. Because my class is not very hard, and so my professor likes to just ask us to do things. But another great time is if you do have like a lot of sources and you're trying to figure out the effect of a source, or you're trying to figure out, just in a much simpler way of trying to deal with, because I mean, even just these, well, okay, these weren't too bad, but you can kind of see how something like node voltage analysis might get a little unwieldy, right, with a lot of equations. A lot of the times node voltage can get up to like 4 nodes, and then you have 4 equations, 4 unknowns, 3 or 4. it's gonna make your life easier if they're all the same source. Because like if you have a bunch of currents, then whoa, you can do either mesh current if they're just like easy currents, or you can do node voltage because they just go into the nodes. Or if you have a bunch of voltages, do node voltage to get you guys some extra nodes, or you could do mesh current because you just add them into them. Anyway, so one thing we're gonna take a little aside before we do the next thing. We're gonna talk about dividers. This is a pretty simple. It's almost like a trick. I don't want to say it's a trick. It's kind of a trick. It's a theoretical thing, but dividers are great. And honestly, there's a reason why I'm putting them at the beginning of this and not like near the end, which is where my professor talked about them. And I'm like, dude, this would have been a lot easier to use in various things. So when we have a I think it's maybe a little bit easier to kind of visualize with current. When we have current and it's coming in somewhere and it's going to go out to two different places, let's say it's like two resistors, right? And these can be equivalent resistors, as in like you've added a bunch of resistors, or they can just be, you know, one resistor. The way that the current is divided is related to some sort of ratio of those resistors, right? Because like if this resistor is high, but if this one is not as high, more current's going to go over here, right? And so the sort of motivation for dividers in general is by saying like, okay, let's say we have a voltage source and we know resistances, and we want to find the voltage over a resistor. How much does it get? What's the ratio? Like, we want to just be able to say, here's a number using our physical values of our components that we can multiply into the voltage source, and that's what our thing is. So you can see over here, if we just want to find the voltage over R2, and this is sort of like what you do in physics 3, right? Like, oh, I want the voltage over this component. You could go ahead and say like, okay, well, I'm going to combine all them, and I'm gonna, do out my current, and then I'm going to multiply that. But if we actually do that out for this one, here, we'll do that first. So our REQ is going to equal R2 R3 plus R4, right? And so that means that our current is going to be Vs times that. Nope, I lied. Vs over that. Oh boy, it's one of those days. Equals I over R. I equals V over R. Woo, woo. I know how to say words. Okay. And then we're going to multiply this, right, by our, if we want the voltage over like R1, let's say, we would multiply I times R1, and that's going to be like Vs times R1 over R1 plus R2 plus R3 plus R4, like that. And so if we wanted to say what is the voltage being multiplied by, we can see that it's going to be the resistor, and this is for voltage, it's going to be different for current. We can see that it's going to be the resistor over the total resistance. So for a voltage divider, if we have this, we can just say, okay, V source times, so if we want to find V over R2, that's going to be V source, and it's going to be multiplied by R2 over all this stuff added. Easy as that. And that way we don't have to worry about the current, because we don't care about the current. We don't have to find it directly. But we know this ratio, right? And we can easily adjust that. And there's a similar thing you do for the current. So we would say, so there's two different ways of writing it. And you can prove it similarly to how I proved the VS, but like the easiest way to do it is if you have a current source and you have resistors in parallel, like this. I kind of like to write it like we have IS, so let's say this is 1, 2, 3. So like I of 1 equals IS times 1 over R1 over 1 over R1 plus 1 over R2 plus 1 over R3. Because this is what this is saying to me in my brain is like, okay, well, we know voltage is this, and we know like current is sort of, it's not the inverse of voltage, but like the way you do it, you're dividing the resistances instead of multiplying them. And so it's like R1 to the minus 1, and then REQ to the minus 1. And in this case, right, our REQ is 1 over R1 plus 1 over R2 plus 1 over R3 to the minus 1. So if we have the minus version of that, it's just going to be all of them added. Another way you can write it is if we say, and this only works for 2, or I've only seen it work for 2, it might work for 3, but if you have like 1 and 2, you can say IS times R2 over R1 plus R2 to get the current for I1. But I just, like, these give you the same thing, and the first one that I showed is expansive to 3, definitely, or more. And I think it's a little bit more intuitive to kind of remember why that works, but yeah, either one works. But these are really great to just have in your back pocket, so you don't have to find a bunch of values you don't care about. That's the idea. Okay, cool. So we did dividers. All right, this one is going to be a little tricky. So sometimes in circuits, yeah, that does seem pretty nice. It's great. So similarly, this thing is kind of in the same vein as that. A lot of the times when we're analyzing circuits, there's just a bunch of shit we don't care about. That's kind of the common vein of this course. You want to be able to, like, if you're an electrician, right, or if you're a person working on circuits, you have like a massive circuit, and you only want to really work on like one part of it, right? So sometimes you just want to say, like, I want to focus in on like this one, like maybe 3 like loops or something, and I just want to pretend all the rest of the circuit is really simple, right? So that's like saying, like, I basically don't care about anything except the thing I'm working on. And, you know, we like doing that because if you have a big thing, then you don't want to do that. Now, I will say, for our purposes, there's never going to be a time when you will actually use a Thevenin to do that in a class like this. They will not give you a massive circuit and say, like, okay, we'll reduce those to its Thevenin equivalent. Like, we can talk about, I'll talk about like what we need for a sort of equivalent circuit, and then we can talk about like why that would never happen and how people do actually use Thevenin equivalents. So this is called Thevenin equivalent. There are a couple different kinds of equivalent circuits, which is essentially saying, like, let's take, you know, a component in the circuit, and let's take everything else in the circuit and say, what does this look like to that component in the simplest form possible? It's like, we're the 3 ohm resistor, right? And we're looking at the other circuit and we're saying, okay, well, what is this? It's kind of like saying, you know, like when you find the equivalent resistance, if we have a bunch of resistors, functionally, it doesn't matter if those resistors are 4 resistors or 1 resistor because they're providing the same resistance. Obviously, heat and other things and wire exist, but you know, we want to find something that's theoretically equivalent. And so there are a couple different ways we can do that, and they're kind of based off of the power sources. In a class like this, you know, we only covered Thevenin and Norton, which are just 2 funny names of people who made them up. So a Thevenin equivalent is going to use a voltage source, so that's going to be Thev. And I'm actually not going to talk about Norton today because my professor just decided we don't need to know it. So we're not putting it in the speedrun. If we were doing 110% speedrun, we'd do it. But a Norton uses a current source. So let's talk about what a Thevenin needs. So to have a Thevenin equivalent, we're going to need a source of power, right? Assuming that, like, I mean, this is not, I mean, you can do it on a power source, I guess, but like there has to be another power source, right? Because we're going to be getting rid of all this stuff, and it's kind of got to function on its own. So we're going to have we're going to make a circuit that looks like this. So we got a voltage source. We're going to have an equivalent resistance like this. It's going to be called R Thev. And then we're going to have our load right here. So in our case, like, the load is literally just meaning like what thing we're looking at. So like this is going to be 3 ohms in our case, and we know that. That's not an unknown. The load isn't going to change. But it is something where to have a feminine equivalent, we need a source of power. Yeah, this is the girl boss circuit, actually. You can only have girl bosses in EE. That's a rule. Strong, independent woman who wields a current of 1 amps and can and will kill you. But so like another great thing about Thevenins is like if you wanted to switch out your load, like let's say we didn't want this to be 3 ohms, let's say we wanted this to be, I don't know, 4 ohms, let's get crazy with it. We can treat this exactly the same way. Like the rest of the circuit is not going to change because we've just made an equivalent to the rest of the circuit that doesn't include the 3 ohms. So the things that we need to find are we need to find this voltage. It's not going to be voltage source, it's going to be a Thevenin voltage. And we need to find this resistance, right? So the resistance is kind of, it's a little bit easier to understand. It's going to be like REQ. So what we're going to do is we're just going to, okay, I drew garbage all over this and I don't want this garbage here anymore. There we go. Oh, also, Blaine, I'm not doing non-EE questions today because I am doing a speed run. But if you want to, after I'm done, I can take some random extra questions if people want to ask questions, or and I'll just like cut it out of the video, or whatever. Okay, so we need to find resistance. So our first step is we're going to take out the load. Okay, so we're going to redraw this circuit and we're going to just say, what if the load wasn't there? Because we don't want that load to be interacting with this stuff. So basically we just do this. And this rate is actually going to be equivalent to, I don't know why I did that. It's going to be equivalent to if we didn't have that other resistor there, right? Because no current is going to flow through that. Okay, I don't know why I made that one too. There we go. This is what our little duder looks like. Pretty simple, which is already great. Like, I mean, this is like a lot of things. I mean, it's not really that hard. It's like parallel. So we want to find the equivalent resistance. This is not going to be included in our equivalent resistance. And that might seem a little illogical, but it's like because that isn't, when we take out the load, that isn't existing like as a source of resistance, right? Because the current's not going through there. So our Thevenin resistance is going to be 5 plus 4. Let me check that that's right before I say all this. Let me check that I wrote this right before I bullshit all this. I swear I'm not bullshitting, okay? I say after I said I was bullshitting. Where's my Thevenin stuff? I just want to make sure. You guys are getting the top of the line. Where did I put it? This one? That's superposition. Oh, that's where I stole superposition from. Never mind. I thought I just... well, they're in parallel. Okay, whoopsies. Wait a second. Oh, okay, never mind. I'm goofy. We also need to short the voltage source. There we go. Okay, so we're trying to find the equivalent resistance to the load. So we're not that. Don't look at that. That's if our source was the load. Our source is not the load. What this is gonna look like is it's gonna be 1/5. This one. Plus 1/4 to the -1 plus 1. So we do actually have that resistor there. Might be everybody. Because we want to look at what it is to this, right? If these were all just one big resistor to this guy, what would that be? But you have to short your voltage, or in the same way that we got rid of the sources for superposition, you would have to open a current source. So that's going to be our Thevenin equivalent. And then to find the Thevenin voltage, we want to find the voltage over the load. That's all it means. So we're going to put the voltage source back in there. I'll do it over here. Right here. Boop, 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 boop. And we want to figure out what the voltage over this is. So we can do a little funny. We know that the voltage of this is going to be the same as the voltage of these guys, right? So if we take if we combine, or is that the way that we want to do this? Let me see. I think so. Oh yeah. So because we can actually apply our voltage division thing here, because there's no current through here when this is open, right? This resistor is not gonna affect our Thevenin voltage when we're looking at our equivalent voltage. So we're just gonna say that this voltage right here, this 4 ohm voltage of the 4 ohms equals our voltage over our load. So it's sort of like the branch, right? Because there's just no current, so that dude is just chilling out there. Alright, so the way we do this is we'll just say like V source. I'm just going to do it in terms of symbolically, because we can use our voltage division. So because they're in series, we're going to say that it's 4 ohms. Okay, I immediately started doing it not symbolically. Over 4 ohms plus 5 ohms. And then if we want to draw our Thevenin circuit, we would say this. We would draw a little resistor, we would draw our load here. I draw it like that. It doesn't really matter how you draw it as long as you label it. So that's our load, that's really easy, hopefully. We have our R Thevenin here, and then we have our V Thevenin here. And honestly, like, if you can do Thevenin stuff, you can probably do everything else. You'll probably know how to set up, you know, node stuff. Now, you know, getting the answers right is different just because it's a lot of math. I would heavily suggest using matrices for any node voltage and current, mesh current stuff. Because you know, that's too many numbers to be doing. You can't be doing that. No, not good for anybody's health. Okay, we've made it. It's actually, I think we're on pace. I was worried. I think we can do it. We're gonna do the second hour is AC. Okay? So before we get to AC, also symbolic solvers help a lot. Oh yeah. If you have access to like, that stuff. I'm more saying like test environments, but that's just for me being goofy. Did I copy something? All right. We're gonna talk a little about inductors and capacitors. So, okay, here's the deal. You can also use Thevenin and Norton equivalents to bias BJTs? I don't know what those are. What are those? Let's see. Bipolar junction transistor. Wait, that's so cool. It carries both electrons and electron holes? What's an electron hole? Are they still their function as a switch to amplify, filter, and rectify power? Whoa, that's crazy. I don't know what an electron hole is, but that's so funny. Oh, a hole is a positive charge. Oh, are those not positrons? I thought, maybe because I think about them in terms of nuclear stuff. Okay, before we, well, let's say this. So, you probably in physics 3 you talk about capacitors more than you talk about inductors. So maybe let's talk about a capacitor first. So, this is like a very scuffed discussion of transient response. Okay, so that's the academic, like, formal name for it, which is basically just saying what happens to shit after a long time, or as a function of time. Carries electron holes and asks to switch. What are we doing here, Jamie? Doing electrical engineering, baby. Holes migrate? What? Oh, they're like a missing electron. Whoa, that's so cool. Not really, but it practically acts that way. Wait, that's awesome. I love that. Wait, it's literally just like a hole. That's a great name for it, because it's a hole where an electron isn't. Okay, so what was I saying? We're talking about, oh yeah, shit happens after some time. Okay, so we know that a capacitor is gonna store charge, right? And we know that an inductor is gonna store charge. A capacitor stores charge through electrical potential, and an inductor stores charge through magnetic potential, right? It makes a magnetic field, and then it uses that magnetic field to like push electrons around, right? Capacitor is just like its voltage pushes stuff around. So when these things are charging, we want to find equations for that, and they can get a little funky. But I'm gonna only talk about the one equation that works for all of them. Okay, so when we have let's like draw some stuff first. So when we have an inductor, let's do a capacitor. We have a capacitor and it's charging. Let's say that it has some like 0, right? If it's, let's just say it's a capacitor kind of like connected like this to a voltage source. It's okay, put a resistor in there so it doesn't blow up, you know. There's a switch somewhere. I don't know, here's a switch. When the switch is open, right, there's not going to be any charge on this capacitor. It's not flowing around, we're not charging it up. And then as we close the switch at t equals 0, it's gonna, I'm sorry, this t equals 0. It's gonna jump up, and then it's gonna get to a point where it has too much charge, and then it kind of stops. So it's an exponential jump, right? So it's gonna grow very, very fast, and then get up there. And it does a similar thing for it discharging. It's gonna go like that, right? Similarly, it's gonna go like down pretty fast, and then go to 0. Same thing happens for an inductor. So this is about the like, you could say this is the Q on the capacitor. Saying like the voltage of a capacitor is a little trickier, but again, this is more for like just kind of visually thinking about charging and discharging. Like this, you could kind of, I mean, because you're not going to be like, I mean, at least for a course like this, like my course, like we don't graph these things, so really functionally, as long as you you know what it looks like, you could just be like, this is the energy on the capacitor, you know, like it's not really true, but like it's kind of true. It's like how much charge it has, it's how much stuff it has, right? Like that's how far along it is. You can even think about it in terms of percentages, right? Like what percent full is it? So that's our sort of basic idea of, and hopefully, you know, we've kind of seen that before in terms of physics 3. I think we kind of talk about it, but we usually talk about the charge on a capacitor in physics 3 versus now we want to talk about the voltage of a capacitor. So one thing we do need to know is that like when fully charged, what things act like. So when a capacitor is fully charged, when it's like slurped up all those good electrons, you know, as it does, they kind of get stuck, right? They can't cross over to the other side. They get stored on one plate. What am I talking about? There's like too many of them, and so they can't cross over, and so it acts as a short circuit because it stops these guys. They say, stop, don't come through. And they go, okay, we can't come through. It's like a bunch of people blocked up us if they were all standing in the door, you know? Like they're kind of stuck. They can't go through there, so it's gonna act like a like an open circuit. And then for an inductor, when it's full, it's actually gonna act like a wire. They just go straight through. Because an inductor isn't really stopping. Like there's nothing that would physically stop the electrons from moving through. So it's chilling. It's chilling. So as it goes to infinity, right, in its state, it's either gonna, I mean, it's not like if you have 0 charge on it, it's not gonna do anything, right? Nothing's happening, so nothing's moving for both of these guys. But as they go to infinity, this one's gonna act like a wire, and this one's gonna act like an open, not a wire, like a hole. So in this case, it's asking us about like initial and final conditions, right? And So the thing we should throw out here is there's a couple, like there's various equations that you can use for an inductor about, or inductor or capacitor, about their current or their voltage. But callback, whole reference, love that one. But the one that's the most general for like, you can use like for any kind of situation is this one. So let's say, so an inductor is gonna have a current on it, sorry, not a current, a voltage on it of L, its inductance, times the current going across, the change in current going across it. And this is more, again, this is for AC stuff, so like don't worry about that right now. But its voltage is going to equal that. And so if we want to find its voltage in terms of like an equation, we're going to say that it's going to be the V of infinity plus the V right after we change to the new state we're going to, minus the V of infinity e to the negative t over tau. And tau is a time constant. For an LC circuit, tau is a physical property. Tau is sort of, if you watched, I don't remember if I streamed this, maybe I did. If you watched my like Excel streams, if you remember the thermocouple response time memo that I had to write, right? It's kind of like saying, what's your reaction time, right? Like how quickly can you react to something? Time constant is just saying like, how long is it going to take from us to get from point A to point B to a point where we stop, like we've stopped changing, we're steady state, to our other steady state. So our time constant is going to equal 1 over L, or it's L over C, I believe, L over R for an LR circuit. And then for our capacitor, we want to find like the current, right? Its current is going to equal, for capacitors we have, I don't know why I wrote C, that's not current. I equals C dV dt, so it's going to be dependent on the change in voltage over the capacitor. And again, this is for AC, but just so we know that we're looking for current, it's going to be I of infinity plus I of 0 plus minus I of this. Okay, and its time constant is going to equal RC. These are all like equations, you know, you might have to use different ones. There are more specific ones. So like for example, there's one, if it's an inductor and it's just discharging, we can say like the current equals I love the end stuck he just sends. Wait, what is this little guy? Oh, it's just end stuck for gore. I love that you send that every time my mic explodes. But yeah, we can just use these equations down here and just kind of plug in whatever we need if we find the steady states. So one other thing that we kind of gotta check out with these functions that we can learn is when we, let's say we have a charged inductor and we plug it into something that's going to discharge it, right? Like, so we plugged it in, we charged it up, we're going to plug it into like a resistor or something. We need to figure out what is going to jump and what's going to not jump. So in this case, we see that our voltage is dependent on this di dt. So for an inductor, our di dt has to be a differentiable function, which means it has to be continuous, right? And this is like calculus stuff. But essentially it has to not be, like we can't say that we just go from like 0 to 1. We can't do that. So we know that current is going to be the same for if we have I0 minus, it's going to equal I0 plus. Now for the voltage, like we can't say that for an inductor. But for a capacitor, it's the other way around, right? Our voltage is going to be continuous, but our current can change. So like our current is going to actually change directions in a capacitor, right? When discharged, it changes directions. And that's why we have that, because our voltage is the thing that's being kind of physically constrained to be the same, right? Because if you think about a capacitor, we have all these electrons on here creating this voltage, and when they start going off, like they're not just going to all disappear. And then for an inductor, right, like our magnetic field is based off of, you know, our electrons and their position, movement, and stuff, and so it can't just leave instantly because like there's still electrons in there. But the voltage over it isn't constrained by that. Okay, so we got that. So we got to use this stuff to just kind of, we're going to be looking for voltages, we're going to be looking for currents, and then at different times. So based off of the fact that we know, you know, an inductor is going to go to a wire, a capacitor is going to go to a short, an open, and, you know, based off of some other sort of analysis principles that we've been using for DC stuff, we're going to be able to find the values we need to plug into these equations, and then we'll be chilling. All right, let's see this problem. So it's asking us to find the final conditions on IL and V3 in the given figure. Okay, so that means that once we hit a steady state, and in this case, we start with switch closed, and we're gonna open that switch, right? So when we open the switch, we gotta draw the circuit. So the switch closed looks like that, looks like this. We open that switch, that voltage source is going to go away. So we're going to have an R, an L. I'm drawing it kind of too far down. Here we go. And then another R. Did I really give this question? Okay, well this is a very easy question. I might need to pick another one to do after this. But this inductor is just going to discharge until it's done, right? There's no other voltage source in here. So the inductor is sort of providing all that jazz for everybody. And so once it's out of charge, and then we're just done. So if we were trying to write this equation, oh, actually, you know what? Maybe we can write this equation for this inductor here. So at the beginning, we know that for an inductor, the current on it is consistent. So we just found that I infinity, this is going to equal 0, which is great. But we can figure out how much it's going to start with, and then we can plug all these things in. So we're going to say I of infinity equals 0. And to find what we start with, we're going to say, okay, well, we need to figure out what the inductor acts like at the beginning, and then we can figure out this equation for it. So in this case, because it acts like a wire, this resistor just gets got, unfortunately, and it does not get anything because electrons are always going to choose here because they don't want to go to any trouble. So now we can redraw this even more, and look at this. We have just a little funny current divider, like a classic little guy. Unfortunately, we are given a voltage source. That's not super useful, but we can just do, I mean, we don't really even need to do a current divider because we can just say I equals V over R, and we know those things. So in this case, we're trying to find the current through this one. So we're going to say it's going to be V source over R2. And whatever those values are, we would figure that out. And so we'll say I 0 plus, so right after we throw that switch, what is its full charge? That's going to be S over R2. And then we're going to want to find an equivalent resistance as seen by the inductor also. For this R, that's not the right one, for this one. So it's kind of the same thing we did with the Thevenin. So we're going to replace this with a open circuit, and then a womp, womp, womp. Yeah. So So we'll combine those two, so it'll be R1 plus R2. And then because these are connected like to the ends of each other, they're in parallel. So it's going to be 1 over R1 plus 1 over 2 minus 1 will equal our R. And then we have everything, and we just can plug it into the equation, and we can, then we can plug in like a T, right? And we can say like, oh, the inductor is going to have this much current at this time. That's kind of exciting. Kind of fun. But yeah, I mean, the final state of both of them is just going to be 0 because they're going to discharge. So, you know, we don't really have to worry too much about that. All right, so we just talked about, oh wait, this one. Initial and final conditions on IC and V3. We could look at this one too. Oh yeah, for capacitors, yeah. Oh, and look, this one is asking for the initial and final conditions, so. Okay. Here we go. Make it a little bigger so you guys can see it better. I can see it better with my old man eyes. All right, so this is kind of gross looking, but this is also a good example of circuits that kind of look weirder. In this case, these are all ground, so they're like connected like this, or you know, like this. But they're not always gonna be. It's not always gonna be drawn like that, you know. So at the beginning, our circuit is gonna. We should draw what our circuit looks like. So it's gonna look like this. Boop boop boop. Boop boop boop. And then our capacitor, like that. So in this one, they're asking for IC and V3. So this one's great because the initial conditions, V3 initial equals VS, right? Because that's just in parallel. We can just copy and paste that voltage. And then for IC, it's also pretty simple. We just say, we want the voltage of this this branch, right? Which is going to be VS1 over the VS over R. R2. So that's pretty nice. All right. Those are our initial conditions, and then we got to check out what our final would be. So we actually have two, you see we have two different voltage sources here, which is like totally okay. We're just going to use different values when we come to our steady state. Now, so this is kind of interesting. We haven't exactly talked about this yet, because it's a little complicated, but so what we were talking about before was sort of more of what's called, VS is VS1. Yes, VS is VS1. We were talking about a what's called a natural response, which is essentially this idea that if you leave stuff alone, it's going to do something, right? So when we let an inductor discharge, right, that's going to be sort of the way that it works. But in this second state, we have a voltage source kind of prompting the capacitor to do something, right? And we actually call that a forced response, because we're kind of forcing the capacitor to, you know, to do something. We can still use the same equation up here, because this equation is just a general equation for a forced response, and it can also talk about a natural response, right? So in the case that we saw, with a natural response, you're going to have 0 current at the end of it, like for an inductor, and so that's just going to go to 0, and it's going to give you the same sort of equation that you would have with just the specific one. Okay, well these taus are for, this is like for an inductor, and this is for a capacitor, so we're clear about that. It doesn't really matter which one of these, because it's a general differential equation. The setup for both of them is the same. So I'm not gonna solve it. I didn't prove it. You just kind of have to use it, unfortunately, because differential equations is not a prereq for this class, so nobody gets to do anything ever. Anyway, kind of depressing, but that's okay. So we can draw our circuit for our final little whatever. That was very vague. For our final conditions here, with our new friend, the voltage source, or other voltage source, and then we'll just find that, okay, as our capacitor fills up totally, oh, also, wait, nobody caught me on this. The IC is not this. IC as it's charging will be this, but at the initial condition, at steady state, this is gonna be 0. Poggers. Because as we hit a steady state, this is gonna act like an open circuit, and that's the same for this one. So this is gonna act like an open circuit, and this is gonna just not be here. So the final conditions on IC both times are gonna be 0. But if we were trying to find you know, V of C or something, right? Like we would do a voltage divider for the resistor, and we'd figure that out. Anyway, there we'd actually have to do QVC stuff. I don't think we can just do a voltage divider because it's not like a resistance. That's kind of unfortunate, but we're not really gonna have to do that ever. But IC is gonna be 0 again. And in this case, we would just do a voltage divider over these two, because now we have a resistor here. That's the only thing that changes. This goes away because our capacitor, I'm gonna put it as a ghost. Our capacitor ghost just, you know, acts like a short, being a silly little guy. So it'll be V3F equals VS1, and we'll say, what is that? R3 over, and they're in series, so it's okay. R1 plus R3. Sorry, that's VS2, not VS1. There we go. Yeah, initial and final conditions, they're kind of just like regular analysis you would do of the transient stuff, but you might have to plug them into an equation, is kind of what it ends up being. All right, now we get to talk about fun stuff. We're nearing the final. I think we can do it. We're gonna talk about AC. Okay, I actually have. Okay, let's talk about this. So, AC is not that different from DC. It's a different type of power, right? So for DC, the definition, or like what it does, is called direct current, right? It's gonna just go in a circle around a circuit. If we have a circle like a circuit like this, it's gonna go around in a circle around the circuit. It's gonna keep going around, just in a circle. AC stands for alternating current, and so what it's gonna do is instead of going in a circle, it's gonna go this way, and then it's gonna go this way, and then it's gonna go this way, and it's gonna go this way. So it's going back and forth, like if you were to take like a motor almost, and you were to kind of run the motor this way for a little bit, and then run the motor this way for a little bit, this way for a little bit, and then run the motor this way for a little bit. And what that does is it produces a sinusoidal wave that we input into our voltage, right? Our voltage becomes a sinusoid, our current becomes a sinusoid. And so we get, and the reason we do this is because like AC is more efficient to travel over long distances, and our whole world wouldn't really function that well if we didn't have AC stuff, because it's really useful and efficient, and we can step it up and step it down and all this other great stuff pretty easily. But this does mean that we have to work with functions now of current, and you know, that's not something that we really can do super easy. Like if we, you know, that would essentially like being saying like, okay, well, we have a cosine of like 100t plus 4, and then also 13, but like put that in your circuit. So it's like we can't really use the same methods necessarily as we have for DC stuff, and certain components are going to act differently because of the changes. Hint, hint, wink, wink, nudge, nudge. Slow stuff. So I do have a simulation that I want to show, but before we do that, I want to just talk a little bit about something called impedance. So when we have an AC circuit, it's not something to be scared of, okay? We're gonna have a voltage source and big, scary change. We're gonna write this on it instead of writing this, because we're gonna input a sine wave instead of a voltage. Well, it's gonna be a voltage, but you know, it's gonna be an alternating voltage. And we're gonna have some components, right? We can have a resistor, we can have an inductor, or we can have a capacitor. And that's kind of it. Scary worm. Yeah, it's the evil worm. He's gonna get you. So these are our three main players. Three big boys. Three strong women. The girl bosses, if you will. And so the way that these things are gonna interact with AC is gonna be a little different, because for inductors and capacitors, their voltages and currents are based off of changes in one or the other. So for a resistor, it's going to act exactly the same. Okay, it's going to be just a little guy, and as the current goes through it this way, and as the current goes through it this way, you know, it doesn't change that much. It's going to change the amplitude of the current, right? Like, we know that. If we put a resistor in there, the current's going to not be as big. But for the descriptions of these guys, they're going to affect the voltage and the current, and we kind of need language to describe how they affect it. So in AC circuits, we're going to kind of switch for talking about resistance. Resistance is apparently I spelled it. Resistance. We're going to talk about impedance. So every one of these three devices has impedance, but not all three of them have resistance, right? So impedance is sort of a measure of how we impede the sinusoids coming in. So how we interact with them. For a resistor, it's going to be, so we call it Z instead of R. And for a resistor, Z is literally just going to equal R. Which sounds a little funny, but in this case, it's just real. It's a little weird to think about, but when we think about impedance, what we need to describe. Okay, so let's talk about this first. When we have a sinusoid coming in, it's going to have an amplitude and it's going to have a phase. Okay, so when we have let's say we have 10 volts coming in of cosine, and I'm just gonna say an omega. Oops, you can't really see that at all. Gonna have some frequency, right? Let's say 100. I don't know. T, right? Because it's gonna change based on time, and it's gonna have an angle of 0 degrees. So first thing is, we're always going to define everything in terms of cosine, and the way that I like to think about why is because when we have 0, cosine is going to equal 1, and it sort of works out well for us that it equals 1, because when sine comes in and it equals 1 later on, we can kind of see that sine is going to push cosine around in a weird in a way, not in a weird way. But it's good to think about their relationship between each other, right? That sine is cosine like plus 90 degrees. So we want to keep everything in terms of cosine, because our cosine is just like, its base level is 0. It's 1 at 0, which is great for us. So we can write this in terms of this, right, as a cosine, or we can use what's called a phasor, which is a great word. It's a different form of writing something. There are lots of different forms of writing things. What we're going to do is we're going to take the amplitude, because we care about that. We don't care about the cosine, so we're not going to write that. We don't care about the frequency. Well, I mean, we do care about the frequency, but not in this. We're going to get rid of that. We only care about the phase angle. So we write this is like a little vector, like angle sign, and there's our angle. So if we want to write this, it's going to equal that. If we want to write, let's say we want to write like 20 sine 100t. well, first we have to change into cosine. So it'll be 20 cosine 100t plus 90. And then we'll have 20 at 90. Like that. There's always cosines. Alright, back to impedance. So impedance is going to affect the amplitude, but our impedance is actually also going to affect the phase. So when we have components in here, right, if we're sending in a wave that's kind of looking like this, we might have some guy going like, no, slow down, speed up. This guy goes, no, I want you to speed up, don't be so slow. And the reason why we sort of talk about them in real and imaginary terms, generally what we do is we say like, okay, so impedance is going to have a real component, it's going to have an imaginary component. It's like Z equals R plus X EQ. And this is, you know, reactance or something. It's a word, it doesn't really matter what it is. This part is the real part. This part is the real resistance that's changing the amplitude of our current that's going in, or voltage or whatever it is. But you also have this fake, this not as useful part, which is going to change the phase. So for us, the phase doesn't really matter in the sense that, like, if we sent a thing at like a certain phase through this thing, it's not going to change like the power we're getting out of it, right? But what is going to happen is if we have like a wave going in like this, and we have other waves kind of going against it at different phases, we are not going to get the maximum amplitude of this, right? So ideally we want our phases to sort of be the same so that we can get maximum things. But that's why we have a real and imaginary part to our impedance. We have to think about the phase angle. All right, so we've got this. You can actually also write impedance as a phasor by saying, because impedance is like a vector. This is kind of all over the place. Sorry, this is definitely not my cleanest moment. But if we want to graph impedance on, also, you know, just to add insult to injury, for some reason, not for some reason, in EE, right, the imaginary number I equals current. So we can't use the imaginary number I. So instead of using I, they use J. Just because. That's what we do. So if we're trying to graph something with our real axis here and our imaginary axis here, which it kind of doesn't really matter that it's real and imaginary. It could be like X and Y, who cares? Just so happens that ours is like this imaginary sort of thing that's changing phases. Although, again, it could just be X and Y. But it just so happened that they're like, this is imaginary. If we want to graph this as a vector, right? Because I mean, like, all these are vectors. Or this is like a vector, right? It's 10 at 0 degrees. In our case, we would say, okay, our R is going to be here. And let's say our impedance is up here as our X EQ. This is the imaginary, the J axis. Then our vector would be here, so we can find this angle, and we can write it as like basically R squared plus X EQ squared square root. And then our angle of, like, I think it's tangent XEQ over R, however you want to get that angle from the trig. We're special. J is derived from the same letter, the letter I'm pretty sure anyhow, so it's really the same thing. Smiles. Well, I'm glad to know that you guys aren't just wonderful, special people, and you really, truly have reasons for things. That's exciting, though. I was told it was just because I was already named. So yeah, we can write phasors, you know, in terms, basically phasors are like vectors. And if you want to think about, there's a cool thing you can do in the imaginary and real axis by saying, like, all right, if we have a circle with a certain radius of like 10, and we have a changing phase angle, when we draw this out, it's gonna, when we draw it along the real axis only, it's gonna draw a cosine wave, which is what we actually get from the thing. So that's kind of a cool way to think about it for phasors, like how they create the cosine waves. Actually, it comes from the French equivalent of current intensity. That current is called I. Huh. I did not know that. I thought that, I mean, I knew that it was called I didn't know why it was called I. All right, so let's do, I'm gonna pop over to the simulation I have so that we can take a look at how a oh god, I hope it wasn't on long. So if one of these, I'm just going to do a voltage connected to a resistor, and we can see it's kind of going wibbly wobbly back and forth. And then this one, I'm going to do the same setup, so we connect to a resistor, but I'm also going to throw an inductor there. So now we're going to use, I'm going to pull out this little current chart here, so we can see that the current in this one and the current in this one, if we put them right on top of each other, their magnitudes are different, right? Which is going to be dependent on that impedance. We haven't talked about how to like calculate the impedances yet, but we can see that like they're still going up and down at the same time. Because that's because the inductor, right? We have that it's based off of the change in the current, so it's not gonna mess with the it's gonna mess with the voltage, not the current over it. But if we take a look at the voltage charts for these, for this one, it's gonna be like that. For this one, we can see that they have the same amplitude, right? Which makes sense to us. But wait, why are they going at the same? Hello? Wait, go over here. Wait, why is it? Hello? Why is that not changing it? Okay, well, that's, That's so weird. Okay, when I did this, literally when I did this earlier, it was doing it correctly. Wait, this is so scuffed. Why is this? It's, okay, well, that's not useful at all then. That's so goofy. It's supposed to show, like, so the inductor is gonna, push the voltage back. Wait, did I set this up any differently? No, I set this up the same over here. Wait, let me check over here. Sorry, technical difficulties. Let me see on this one. Yeah, they literally. Okay, maybe I put them on the wrong side or something. That could be it. Wait, sorry, let me check. Oh wait, is that what I did over there? Maybe I did that, and that's why they're off. No, they're. Oh, that's maybe why. That's so goofy. I don't know why they're. Okay, well, what it's supposed to do is show that the inductor lags the voltage, and that if we were to put a capacitor in here, it's gonna make the voltage phase go forward by 90 instead of the inductor. Well, Okay, that was a fail, but that's all right. Thanks, Pet Simulation, for not being my guy. Oh wait, did I connect them to the wrong? Wait a second. If I did that, no, that should be the same. Just trying to think if I connected them this way, it might have just like. Okay, I'm gonna do this for 3 more seconds, and if it's not, yeah, I don't know why that's so weird. It's because I just did it over the voltage source change. Start for it. Okay, well, that's 0. That's. Oh wait. No, it's not that. Okay. No, yeah, never mind. Don't worry about it. Don't worry about it. Okay. Anyway, we don't even really need to worry about it too much because we're gonna be like adding phasers and stuff, and subtracting phasers. But it is kind of good to know that like. Okay, if that's simulate, that's so sad. I'll probably just cut it. I love doing live stuff. When you have an inductor, it's going to sort of pull the phase back, and when you have a capacitor, it's going to push the phase forward. It's just the physical components. There's a little excerpt I found on that I thought was a good explanation, which would be here. Saying. So the inductor's changing current is what makes its impedance. When the change in current is the greatest, the reactance will be the greatest, or the impedance will be the greatest, and the voltage will be the highest. But when the change in current is 0. So when we have the current lagging behind the voltage for an inductor. It's a little weird. Conceptually, but again, it's sort of just like we're gonna see it when we do impedances and those kind of analyses, because that math will kind of back up that. But you know, so for doing impedance stuff, it's just the same as doing resistance stuff, except that we just treat every component the same. So because they all have impedance, if they're in series, we're gonna add the impedances, and if they're in parallel, we're gonna do our 1 over impedance and then to the -1. Okay, let's do. We actually did that one already. Okay, let's talk about this. So with impedance, it means that we have so with impedance, it means that we have a certain amount of power that's going to be dedicated to creating real, like, power that can go and be used by our loads or resistors or whatever. But it's also going to create a certain amount of power in the circuit, or like current or whatever, that goes toward changing the phase. So it's really useful for us to figure out what power is going to changing the phase versus what power is going to actually be useful to us. And that's why we use that sort of real and imaginary setup, because all the bits that's here. Okay, so let me be a little bit more clear. This is generally when you draw this and you say like, okay, we have real here and we have the imaginary over here, and we draw an impedance, right? So by this saying real and this saying X equivalent, this is called an impedance triangle, which is just a name. I mean, it's just a name for it. It's a phasor, it's triangle, whatever. Vector, lots of things. But we can see that this is sort of, this angle is representative of the ratio of our real resistance to our impedance, right? So how much of our total bit is going to one or the other. So when we're using, when we're trying to compute power stuff, which, power is just V over I, that's the same. We're gonna actually use a very similar triangle called the power triangle. We're gonna have a real power, and we're gonna have a fake power, and then we're gonna have some form of the combined power. So this is called complex power. the one that's them together, which kind of makes sense. It's the complex number. Then we've got our, generally this is called average power, or it could just be called like real power. But we can find an average, you know, based off of it, depending on if you're using VRMS, which we'll talk about a little bit later. And then you have over here on this axis, right, like this is your average power. You have what's called your, what is it called? Apparent power. It's kind of a weird name for it, because it's kind of like, you'd think that this would be the apparent power and this would be the, I don't know, but complex is the together. And the fun thing about this is this angle is actually the same angle as our equivalent, so this is our ZEQ for the whole circuit, our equivalent impedance. And that kind of makes sense, right? Because it's the ratio of the real resistance we're putting into our sort of like resistance or impedance that's going towards just changing the phase, which isn't gonna be helpful to us. So for this problem up here, it's asking us to compute the average power dissipated by the load seen by the voltage source. All right, so they give us a voltage source. So we've got our first little phasor out in the wild. They're giving us an omega as well, just in case we need to calculate some stuff for that. Let me pull up the numbers so I can give some numbers and check them. That. This. Oops, not that actually. This. Clicking simulator. Let's see. Is it the first one? Yeah. Okay. So first, let's figure out our impedance. Oh god, I never even explained what impedance was for non-resistor things. Okay, so yay, fun thing. So for a inductor, it's going to be so for inductors and capacitors, they are literally only unreal. They're only imaginary in terms of their impedance that they contribute. And so for an inductor, it's going to be omega times L. Right, so the frequency of the circuit times the inductor's inductance. And then for a capacitor, it's going to be 1 over, so this is time, that's J, right? It's going to be 1 over C times omega. J. 1 over J, right? So it's going to be J at the bottom there. So these are just definitions of impedance for these components. So let's use these definitions and let's do it. All right, so we need to combine these two first. So we're gonna have, and these are just gonna be like components, right? So like we can't add an R to a complex number. We can't, you know, we can't do that stuff. We can't add a real number to a complex number is what I meant to say. And J's actually just function like complex numbers. And if you want to turn a phasor into, you know, a complex version of itself, like you can just do that and then just do complex number math. So like complex conjugates still hold, all that good stuff. All right, so if we want to say R plus our impedance of this capacitor, J omega C, and then it's in series with, or sorry, it's in parallel with this one, right? So we're going to say 1 over this plus 1 over J omega L, or sorry, I'll do this, omega L J, and then all that to the minus 1. And I'm not putting in numbers, right, but this is just our overall impedance for this. This is equals our ZEQ. So that's actually this, right? So when we're trying to find the average power dissipated by the load, and the load is all of these together, what we're going to want to do is say that to find power, what do we need? Let's start with that. P equals VI. We've got a V, we need an I. Or actually, we don't even need to do that. We can just say V squared over R. That'll be easier for us, right? So what we're actually going to end up doing is with phasers, phasers are really great for multiplying and adding. Multiplying and dividing. So when you can turn a phaser into complex numbers by just like doing the sine and cosine of it. And you know how like when we add, it'll like look like a complex number, so we can add these really easily, right? If we say c plus dj, that's just like a plus c plus b plus dj, right? That's great for us. We know how to do that. Multiplying complex numbers, you can do it like all right, but it's a little bit clunky in rectangular coordinates. But for phasers, if we have like, let's say a times a theta times b phi, that's going to equal a b times theta plus phi. So it's very simple for us to do. We multiply the magnitudes and we add the angles. And then if we have a theta divided by b phi, we're going to get a divided by b over theta minus phi. Phi. Fuck. It's not called phi, man. That's depressing. It's phi. It rhymes with pi. Alright. So we got that. I don't remember why we're doing that. Oh yeah. Because, so when we're trying to say v squared over r, v squared, v is a phasor. So we're going to say this equals 50, 0, times 50, 0. And then we can write our ZEQ as a phasor as well. So what we'll do is this will give us a number that's like something like r plus x eq j, and then we can turn this into r squared plus x eq squared, square root at the angle tangent inverse x eq over r. And so we pop this on the bottom here. Oh, you know, the classic number, tan inverse xeq over r. So we'll add these together. This will be 50 squared at 0. And then when we do that, we'll just subtract this angle and everything will be peachy keen. So that'll give us our complex power, right? That's a complex number. And then we can use this angle and we can get the average power from that, which is pretty cool. So we're just using these two triangles and kind of relating them to each other, and you know, as long as we can find the impedance, which is again similar to resistance, we're just going to add it or you know, put it in parallel. We can find how much. We can also find how much power we're wasting. So a really typical question that people would, you know, ask with this is if you have too much. Right, you can kind of see that like an inductor is going to add a certain amount and like a capacitor is going to kind of sort of maybe take away a certain amount. If your power is like, if your angle is really tall, right, you're getting a little bit of power for wasting a lot of the power of your voltage or whatever. And that's not great, right? So a lot of the times what people will do is say like, what theta do I need for this for the power that I need? Or like what theta is like allowed? Because sometimes cities will be like, you can't have, or not sometimes, cities will very often, oh, hello, hi. Trick, oh my god, I'm reading. Trixie, but like with a lot of extra letters. A lot of times cities will be like, okay, Elon Musk, you're operating at 1% efficiency. We're gonna shut down your plant. Like, so you have to have a certain, you know, low enough. I think it's usually like below, or my professor was saying that it was like below your power factor, which is like the cosine of this angle, right? Just if we want to turn this into kind of a normalized thing, it has to be like, you know, 0. Or it has to be like 0.997 or something, like, right? Something very, very high so that it's very efficient in terms of the real power that you get out, because you can't do anything with the power that's changing the phase. It's just gone. It's going into changing the phase. Nobody cares about the phase. I mean, we kind of care if we're trying to phase match, but I don't think we're going to talk about phase matching. Maybe we'll talk a little bit about it. Okay, we are nearing the end. We are seeing the end of it. Okay, last thing we're going to talk about. Okay, I decided we're not going to talk about transformers because I think it's not even really worth talking about transformers because the only thing we do is like multiply them by a number or just use a bunch of equations, which is not really conceptually too interesting. I feel like the Physics 3 conversation on transformers is a lot better. It's like using two inductors, right, to, you know, step up voltage or step it down, which is great. It's super useful, but you know, not super interesting to talk about. All right, so one thing we do have to talk about is we've been talking about phases. We've been talking about, you know, phasors, all this stuff. One thing we haven't really talked about is frequency. So generally what, when frequency comes up is in this thing called frequency response. And it's not really about frequency per se. It's more sort of just like an AC thing that happens. But it is important for us to kind of talk about how certain components will respond to having a certain frequency put into them. A really good example of this is so frequencies are all around us, right? And one thing that's really common is electromagnetic noise in any signal, right? Probably what's happening to my microphone on a day-to-day basis. And if that signal, you know, gets in and it gets, you know, into like an audio thing, or if it gets into an electrical signal, it can like mess with your voltages, it can mess with your currents, right? We don't want that. We want to know what our currents are doing, right? If we're using AC, because we're using AC usually. So it's sometimes we want to build, you know, filters is a common application of this, but they sort of stem from this idea where you put in, you know, a voltage, and you see how the circuit responds. There's more stuff too, but that's kind of what we start with. So we already talked about, you know, it's kind of a continuation of what we just talked about, but just a little bit more about the intricacies. So we're not gonna be talking about like average power. We're not gonna be talking about the circuit as a whole. It's more about now, sort of like what we did with node analysis, right, where we want to find the voltage at a specific place. And yeah. So like in this one, if we put in a certain voltage here, like what voltage are we going to get out because of this inductor and the resistor? All right, let's do it. So the way that, again, it's not really that hard to do this kind of thing because we're really just saying like a fancy voltage divider, right? So the voltage out is going to be the same thing as across this resistor, and it's literally just, you know, a voltage divider between these two components. But instead of using resistance, we're going to use impedance because we're doing AC stuff. So our impedance is omega L J for our inductor, and then it's going to be R for our resistor. And so what we're going to say is it's going to be V source over J omega L, or I say J omega L because it's usually written J omega L, but I don't know. I think if you think about it, a complex number, you know, it's AI, it's not IA. But so then we have it over this phasor. And so we do have a division here, and that's gonna be kind of annoying to work with in terms of rectangular stuff, unless we want to do complex conjugate, which is totally fine. You can also do that. But I'm just gonna turn them into phasors real quick. So we'll have VS, which is, you know, it'll be whatever it is. V in, I guess I should say. And then we'll have omega L Holy smokes, yes. Yep, that's the microphone demon. I'm sorry that you had to meet him so soon to when we were talking about electromagnetic interference. I edit out all of the many times this happens during my my VODs, so VOD watchers don't have to deal, but Twitch VOD watchers have to deal. Sorry, Twitch VOD watchers. Yeah, we're gonna get, when we divide it by the, so they ask for the frequency response, which is V out over V in. You can't see it. I'm glad it's not the end of the world. Oh god. It's pretty bad, I know. When we ask for V out over V in, this is our V out, so when we divide it by V in, the V ins will, you know, go away, and we'll just get a phasor, which is defined as the frequency response. So one common thing, right, is if we want to filter out those things, we want a frequency response where when, like, let's say it's a really high level frequency, but we want to let low level, so if this is our frequency, like, I guess this is our, like, amplitude, and this is our frequency. If we want to say, like, we want to let high level frequency, or we want to let low level frequencies in, but we want to get rid of high level frequencies, we can make a frequency response where as omega goes to infinity, we can say the amplitude goes to 0. Or, like, in this case, saying, like, z goes to infinity, if that makes sense. So in this case, if we look at this, as omega goes to infinity, we're going to have z go to infinity, right? Because it's going to get really, really big. And then if we have it going to 0, then it's going to go to our resistance R. It isn't really, in this case, it's not really like there's like in this case, this is a one that filters out the high frequencies, right? Because, like, as we get bigger and bigger and bigger, the impedance gets bigger and bigger and bigger. But if we wanted to say, I don't know, put a capacitor in here, 1 over j omega c, as omega gets bigger and bigger and bigger, this would go to R, but as omega gets smaller and smaller and smaller, it would go to infinity. So that's kind of how we can think about, like, making filters. There are some filters, like, you know, if you have generally, like, at least the ones we talked about, there's like a capacitor and a resistor. We just showed this one. In this case, we have 1 over, like, j omega c. I don't know why it's so small. 1 over j omega c. If our voltage is here, right? And as we put in high frequencies, we're gonna be good. We're all good to go. But if we put in low frequencies, it's gonna be bad. We don't want those there. But if we actually switch where the voltage is being defined, so, like, this is our V in over here, V in, but this is V out, we can flip it for this specific scenario. So, like, sometimes people will say, like, oh, well, you know, high pass filter, low pass filter, just switch the capacitor and resistor. But it's like, you can also define, you know, like, this one is a high pass filter. Oh, also, if I say high pass, or this is a, low pass filter. Low pass means that, like, low frequencies can pass. High pass means that high frequencies can pass. You can also make something called a band pass, which is, like, if you want these frequencies to pass, but not these ones. Or you could do one that, like, looks like this, right? Like that. yeah, these are really just great for a lot of different things. Audio stuff, electromagnetic noise. They're usually like finding frequency responses is not really too hard. Oh, one thing we should talk about. Okay, last thing actually, I think, which is great. We did it in 2 hours. I was not expecting that. Okay, when we have sinusoids, we have the possibility for resonance. And this is where frequency really comes into play. So resonance happens in a lot of things. Like it happens, it's a thing you gotta worry about bridges, you gotta worry about it in like if you make speakers, if you make anything that's like wave-like. Resonance can be your friend, or resonance can be your not friend. In circuits, a lot of times it's actually our friend, which is kind of cool. Resonance is essentially saying there's going to be a frequency that you can put into a circuit. So let's say like let's just say like a black box sort of circuit here. There's going to be or actually let me do this a little differently. I'm going to put in a capacitor. So this is what my lab finals want. Essentially what we can say is that this voltage source, we're in control of this voltage source, right? Let's say it's like 1 volt cosine. I'll put in a frequency, so it'll be 1 over frequency times 2 pi, I think. Let me think. Omega is frequency. No, 2 pi f. There we go. T plus, I don't know, just plus the R degrees. So we can control this frequency, and essentially for every circuit, there is a frequency that will resonate. And resonance just means that like sometimes it means you take a wave and the amplitude just keeps getting bigger and bigger and bigger and bigger. In terms of resonant frequencies for us, it means that we're actually going to be able to max out usually our voltage, which is great. Over like, so for example, over this resistor or something, we can max out this voltage. Generally, in terms of resonant stuff, I would say I actually ended up doing a lot more in my lab than in my lecture. And just in terms of like playing around with saying, okay, well, so the resonant of the frequency of this circuit is going to be, this is a bandpass also, by the way. So like it's going to be a filter. When we have both a capacitor and an inductor, it's going to be something like kind of like this, maybe. That resonant frequency is the middle of that that we're letting through. There's a lot of other things that you can kind of talk about with this. The bits that are here and here, and also the bits that are, so not the bits, the points that are here, we call them like cutoff points. These are where the frequency is half power, and anything below half power, that's what we deem as like the it's not strong enough to like affect the circuit. And to find the half power, we actually use an RMS, not just like a divided by half. So to do a root mean square, you will take your like voltage and you'll divide it by square root of 2, or like your frequency, and divide it by square root of 2 to find this. So these are kind of located at like 0.7 if this is at 1. It's a little, I mean, this is a little like in the weeds. You kind of probably won't do this. You can also find like these cutoff frequencies here. You can define also what's called the quality of a filter, which is how pointy this thing is, how much it amplifies this resonant frequency, essentially. So this one is kind of like a low quality, but if we had something that was like this, oh, that's pretty high quality, because you have a smaller amount, right, to like hit that, but you get a lot more amplitude out of it. other than this one. So quality is like the difference between this. You also have what's called bandwidth, which is like the difference between your upper and lower frequencies. There's lots of terminology, lots of stuff for filters. But yeah, the idea is that you can have a resonant frequency, which is a frequency that, like, you know, produces your highest stuff in circuit. You can find a frequency to resonate like different things, you know, like because it's just all about it's all about maximizing. I think it's maximizing power, I want to say, but yeah, like you can find a frequency to like maximize the voltage over the resistor. Like for my lab, we had to set a voltage over this capacitor that we knew, and then say like we want to maximize this resistor's voltage based off of, you know, finding that. You can calculate also, this is the section with like a quintillion equations. I'm not even gonna begin, but like you can know a resonant frequency of an LC, like an RLC filter, by doing like this. You can, you know, the quality is like the omega O over the bandwidth, and, you know, all this other stuff. Differential equations for finding these boys. But yeah, I mean, filters are pretty cool. Like, essentially the idea is we want to like cut out certain frequencies. They matter for sure, but when at the end of the day, like, our frequencies are not going to, when we're not doing filters, right, like when we're just doing circuits, they're not necessarily going to play as big of a role, is what I would say. Like when we're doing filters and we're trying to say like, oh well, we don't want these frequencies, of course frequencies are going to matter. But for applications where we're not really, a lot of times like a signal will get kind of like go through something to kind of get rid of the noise or whatever, and then you can do other stuff with it, you know. But yeah, I would say that's a pretty good speed run. It's like just about 2 hours. I would say it's probably 2 hours if you cut out like me talking. If you cut out me talking. If it's just silence, it's actually 0 seconds. So kind of winning. No, fuck my mic. It wouldn't be 0 seconds. But yeah, that's me. I'm planning on doing one of these for engineering dynamics on Sunday, and then we're gonna do one for mechanics and materials on Monday. Mechanics and materials is gonna be great. I'm gonna really enjoy speedrunning it, gonna hate taking the exam. Dynamics, opposite. Speedrunning it is gonna be very hard. It might be 3 hours. It might have to be 3 hours. I don't know. I'm crossing my fingers that we can get it, because I didn't know about EE, but dynamics has a lot. Dynamics has a lot, but like if I can get through rigid bodies, I think we can maybe squish it a little bit. But yeah, I hope this was helpful, or at least interesting a little bit. If not, that's also okay. But yeah, thanks everybody for hanging out. Thank you so much, and Stucky, for rating. You're so sweet to me. So niceies. Also, thank you for oh god, people followed me and I like do not have my thing up. Wait, okay, I need to actually change that right now. Oh no, I do have it up. I just was not reading my activity feed. Okay. Thank you for the follows, everyone. Yeah, I'll be back, and then we'll be on break and we'll play video games. Alright, I will see y'all Sunday. And take a day off tomorrow. Okay. Deal. Bye.